So yeah, we will be talking about hydraulic structures, and in particular, some hydraulic features that are relevant to what we are looking at in here. Starting with this, a hydraulic structure, what is it? Basically, anything that we put in the flow with the purpose of either diverting the flow, restricting, stopping, or controlling water level, or controlling discharge, or managing flow in general is called a hydraulic structure. And how do hydraulic structures do this? How do they divert or restrict or stop on? Otherwise, how is this done? By creating a hydraulic control. So I'm going to write it down. A hydraulic control. So a hydraulic structure, all it does is it actually creates a hydraulic control. And we know what a hydraulic control is. I'm going to write it here, but it's a section where you have critical flow. Your fluid number is 1. So that's what hydraulic structures do. Generally. In some cases, they don't necessarily create a critical flow. We'll see that later today, but that is kind of the general idea. Now, what types of hydraulic structures in general do we have in terms of hydraulic controls? We can look at these in kind of 2 large categories. We can look at weir flow and also orifice flow. So the 2 big categories. The first one, weir flow, is actually overflow type structure, meaning that as a channel bed, we put in some objects, some structures like this to basically block the flow, and then the flow has no choice, has to go over this structure. That's the water level. This is what we call overflow weir or weir type structure and so on. So this will be called a weir in general. So that's one case. The other case is where we have like an underflow. So let's say that's a channel bed. And we take the weir and put it upside down. So if you do that, and your structure now looks like this, then the opening is actually along the bed under this structure. So the flow has to go like this. So that's your water level upstream. The flow is going from left to right, and then has to go through this opening. So it's more of an underflow type structure. These are called gates or sluice gates or slide gates or different terms, but these are really gates. So in reality, these could be a simple plate, really, depending on obviously scale and dimensions and size and so on, but they're really a vertical thin structure, both weir and sluice gate, and they're basically obstructing the flow. There could be another case, let's mention that too, could be a case where you have almost a combination of the two, meaning that almost like you have a weir, and then you have almost like a gate on top. So you only have an opening kind of halfway up in the flow. So if that's the flow left to right, it has to go through this opening, this orifice. This would be an orifice. So all different situations, overflow, underflow, and almost a combination. So we'll look at these and see what is happening in them in terms of the hydraulics. Let's start with the weir flow. Weir flow obstructs the flow is very much like what we talked about when we're looking at humps and choking and so on. So if you recall, what happens in that situation is that if you remember our EY graph, which looks like this, when choking happens, when the flow is choked by obstruction, by a hump or a weir. A weir is really similar to a hump with a much smaller dimension, very, very thin version of a hump. What happens is you have choking and you will have critical flow and minimum energy or minimum specific energy, which is the vertex of the EY graph, as you recall. So I'm gonna sketch a tiny hump as well here. So very much like the hump that we studied. So flow goes over this, it's choked, so becomes critical, and then we get critical depth at the crest. So this will be YC. And upstream is our specific energy, E. So we've seen this. A weir is very much like that. So let's look at the weirs in a little bit more detail. So we remember that specific energy is equal to the in a rectangular channel, Y plus Q squared over GY, 2GY. And if you, again, remember, if you rearrange and look at the critical flow, we'll see that critical depth is 2/3 of the specific energy or minimum specific energy. And we could also look at this and say, if the channel bed is horizontal, your specific energy is the same as your total head, capital H. So capital H here is total head or total energy. And it will be equal to E if the channel bed is 0. So we can continue that equation and say this is equal to 2/3 of H if the channel bed is horizontal and we don't have head loss. That would be accurate. Now, if we continue this and look at and do a little bit of simple math, we'll see that this is what's going to happen. So if we look at our the sketch at the bottom of my slide, right at the crest of this hump or weir or obstruction, whatever it is, we have YC. And then we have a velocity head of this much. Velocity head, so V squared over 2G. As you keep moving upstream, at some point, velocity will be almost 0. It will never be 0 because there's flow, but it will be negligible compared to the velocity at the crest. So we're going to assume it's 0. And then you get a total head or a specific energy of this much. So this will be the same as EC upstream. Now let's look at our critical flow equation, YC 2/3 of H, and do a little bit of simple rearranging of that equation and see what we get. So we know that small q, discharge per unit width in a rectangular channel, is equal to G YC cubed square root. So let's plug in H for YC because we know it's 2/3 of H. So this is equal to G 2/3 of H cubed and everything under the square root. And if we rearrange this again, continue and rearrange and simplify things, this is what we're going to get. We're going to get 8/27, which is 2/3 cube, times G square root multiplied by H 3/2, 1.5. So this is a small q. Now, if we take this and multiply by the width of the channel B, so let me highlight it here, multiply by B, we get the equation for discharge over a weir or a hump or at any kind of choking control, hydraulic control, critical flow that creates a hydraulic control. Now, this is, let me actually highlight that this is channel width. So B is the width of the channel, natural dimension. You also notice that there's a C in front of this equation. That is kind of a correction. Why is that? Because you've probably already noticed we've made a few assumptions until we get here. For example, we noticed that we assume that there's no head loss. We assume that velocity upstream is 0. In reality, we know that these are not super accurate. Yes, velocity might be very small, but it's non-zero. Head loss might be very small, but it's non-zero. So to account for that, what has happened is those are typically not easy to estimate or theoretically evaluate. So instead of doing that, we go ahead with these assumptions and we add a correction to our equation at the end. That C is the discharge coefficient or weir coefficient, as it's called, or discharge correction coefficient, different terms, but it's really a coefficient added to account for all these assumptions. So that's what C is. And you notice in this slide that C varies quite a bit, actually. If you're using English imperial units, it could be anywhere between 2.6 to 4. And if you're using SI, it would be 1.4 to 2.2. In fact, it's worth mentioning that if you do the math and actually do the calculations and look at the equation we have, 8 over 27 times G, and then square root, this will actually be equal to, approximately equal to 1.7. I think it will be 1.67 or something, but let's just use a round number, 1.7. So theoretically, we get 1.7, but in reality, because of all the things we talked about, head loss and velocity, non-zero approach velocity, it might be slightly less, like 1.4, or slightly higher, like 2.2. So that's the range that comes from really field observations and experiments and practical data. But theoretically, it's 1.7. So that's what we have in a weir. Now, the next question is, in practical sense, how do we use this, and where do we see this, and how is it used in practice? So these are structures that we actually see quite a bit. They're very, very common in different scales. They could be a very simple plate, steel plate that you stick in a relatively small channel, let's say to measure flow, because I'm going to go back actually for a second, because the whole point of this weir structure, the hydraulic control, is that it's telling us that if you measure the upstream water level H, which is the head on the crest, so the distance from the water level upstream to the crest, that's as simple as that. If you measure H, you can calculate discharge. The width of the channel is typically easy, right? So we can calculate discharge if we have a good estimate of C. So we can actually use this to measure discharge. That is a very common application. You could basically take a steel plate, stick it in a channel, measure the head upstream, and get discharge. That is actually a practical way of measuring discharge in relatively small streams. Obviously, not in larger streams, but relatively small ones. So that's what we see in this first image A, in this figure. So flow goes over this weir, and we get what is called the nap, and it's basically the flow trajectory, which is almost like a free-falling object in basic physics. It's actually very similar. And it looks like the jet going over this crest, and you get what is called the lower and upper naps. So this is it's called the upper, and then you also have the lower nap. And both of them are exposed to air in general, not always. We'll see an example. And then the flow basically plunges down into whatever's happening downstream. Now, what has happened in practical, relatively larger scales is that really having a very thin structure is not very practical, because from structural and construction limitations and so on. So it's not very practical. So what happens in reality in large dams, what they do is they use the same idea, and they basically copy the lower nap. I'm going to use a dash line to show it here. They copy this and basically use it as a template for the structure right here. So image C in this slide is a practical structure. It is called a spillway. Very, very common structure in many situations, many dams. We have this to control water levels and discharge floods and so on. It's called a spillway, and it basically follows the lower nap of a free jet over the weir. This shape that we have is sometimes called the OG profile. So you might hear that term, OG profile. So that's what this shape is referred to. So it's basically used to as template for the structure, so that the jet is, or the nap or the flow is just sliding over the surface, really. That's all it's doing. Now, continuing on this, sometimes you might actually have a weir, a structure which actually has some thickness in the direction of the flow, like what we have in B, image B. And in this case, unlike the previous case, the thickness of the flow of the structure in the streamwise direction is not negligible. In the first case, A, we have a case where the crest is basically very, very sharp. That's why it's called the sharp crested weir. In the second case, it's pretty thick. It's not sharp. It's has some thickness, and it's called a broad crested weir. So the two terms that you see. Again, very practical, very common in some cases. Some dams and some structures have this kind of weir or spillway, still called spillway, but slightly different arrangement. But in here, the point is the thickness or the dimension of the crest along the streamwise orientation is not negligible. It's some thickness. But nothing changes really. It's the exact same idea. We have critical flow, we have the hydraulic control and all of that, but it's just a different geometric type setup. Now, I have some examples here. Look at this one. This is one example of a crest in a. This looks like a conveying type structure, a canal or something. The bottom, the first one, the top left one, and hard to see, of course, it's underwater, but the crest is somewhere here, I can guess. That's the crest. Let me highlight it. This is the crest of the weir. And by the way, you see there's a hydraulic jump here as well. Not surprising. Whenever we have a, we saw that we saw exact same setup in case of a hump, right? So if you choke the flow upstream, you have subcritical flow, accelerates, becomes critical, continues, most likely becomes supercritical, and depending on what's happening downstream, you may have a jump. This is the case in this image. Yes, somebody's asking if the broad crested weir still is a control and makes the flow critical. Yes, it does. Yeah, again, the details of design and performance is slightly different, but for us, we're not going to get into that detail. And yeah, both of them are basically creating a hydraulic control, which is a critical flow. The same thing happening in the bottom left image. Maybe it's slightly easier to see this one. This is basically the crest. This is the crest. And looks like that this one actually has a OG profile. Hard to see, of course, as an oblique image, but if you cut a section, very likely it's gonna look like this. And the flow is going over the crest, something like that. And then again, we have a hydraulic jump downstream. Not surprising. Again, very, very common situation. When you create supercritical flow, likely you'll have hydraulic jump to convert it back to subcritical somewhere. And if it's designed, you want to have a hydraulic jump. So this is like a relatively small weir. It might be used for water level control. That's very common to bring the water level up. Why? Because you have an intake upstream or you have a pump station upstream and you want to have a minimum depth or, that kind of applications. Or you have your diverting flow to another canal and you want to have enough head so you get the flow you want in the secondary channel and so on. So that kind of applications. You could have by the way, this could be the top left one might be a channel which is, let's say 2, 5, 3, 10 meters wide. This bottom one looks like a bigger one, just looking at the scale and the person standing in the river downstream. This might be maybe 100 meters wide or something in that scale. So quite a bit of a wide range. You could also have relatively small ones. This is something that you might see actually very, very frequently in different places. And when you're on trails and streams and channels, you might see this. These are for different purposes. Relatively smaller. The same idea. You have the hard to see what the crest is. Looks like a curvilinear crest here. Maybe it looks like this. And the flow becomes critical at the crest and then super critical downstream. Write it down. This is clearly supercritical flow. Might be for different reasons. These relatively smaller weirs, this looks like maybe less than half a meter tall or something like that. These could be for different purposes, usually for ecohabitat environmental reasons, like you want some ponding upstream for, species that use this as, for different reasons, or fish or frogs or other creatures. So it might be more of a environmental type aspect of these structures. There could also be, I should mention, there could also be an application where you use these to for stream control and erosion management and so on. Because as you can imagine, the upstream, you're slowing the flow down and you're reducing the potential for scour upstream. Potentially, it could actually start depositing sediments and fill up. And over time, you might actually be changing the slope, the longitudinal slope of the stream over time. Yes, downstream, you're creating supercritical flow, but if you contain it in a relatively small space and convert it back to subcritical, you could use this to kind of manage the stream and control erosion and so on. Here's a couple more. These are slightly different. These ones actually have a cross section that looks like V-shape type crest. So these ones sometimes are called the V-notch weir because they look like a V. And the advantage, these are typically used for relatively small channels and situations. Not that you don't really see these in enormous sizes. They're typically relatively small. Their advantage is that if you have relatively high flow, water over here, so let's say this is a large Q. And if you have relatively low flow, the water will be down here. So this will be small Q. And what happens is that if you look at this image, this sketch that we have, at relatively large Q, you have a large width. And obviously in the relatively small discharge, you have a small width B. Now, if you go back and look at our equation, what this means is that in a rectangular shape, this obviously doesn't change. The width is the same. And what happens is that if you have the same width and very, very small discharge, you get very, very small depth. Maybe difficult to measure, and your accuracy of measurement goes down and so on. So the advantage of these V-notch weirs is that the width changes with discharge and water level, and you get more accuracy, especially at lower discharges. So typically, if you're in a lab or experiments or in a small creek or something, and you want to have a decent accuracy in your measurements, a V-notch is preferred to rectangular. You'll have a smaller capacity, so you cannot measure as high discharges as you could with a rectangular one, the typical one. But again, it's a compromise. You get more accuracy for lower ones. Okay, so these are different situations. I have a clip here I'm going to play. Before I play it, let me highlight a couple of things on this video. So this is looking sideways. Flow is from left to right. That's the flow. And obviously this is the weir. So that's the weir. It's a sharp-crested weir. We see the nap up at the lower and upper nap. And this video is going to show us what happens in general to the trajectory of the flow over weir. So we're going to play it, and maybe we'll need to play it more than once. But okay, that's typical. Flow goes, becomes supercritical downstream. We don't really see a jump here, at least not yet. And what happens here is that these have this kind of space underneath the jet, which is the OG profile, as we saw before. And what happens over time is that the flow is going relatively fast, and it's dragging air with it. And over time, pressure in here goes down. So pressure drops, let's say. As pressure goes down, you get subatmospheric pressures. So that means like suction. So the pressure goes down. So the jet, see, this is the initial stage, is pulled towards the weir. and over time it gets closer and closer. And at some point in this video, it actually sticks to the plate, to the weir. One of the reasons why we have the OG shape for spillways is that we don't want that to happen. So we basically put concrete or some kind of structure there to copy this shape, the OG shape of the lowered nap. So we don't have to worry about this. See, the pressure goes down, and look at this. The jet is actually just sticking to the wall. It's not even separating from the wall at all, because pressure is negative. There's suction underneath, right? So there are ways to prevent this. One way, as you can imagine, is somehow pumping air under the nap, not pumping, but supplying air with pipes or what is called an aerator, which basically supply air underneath, so the pressure doesn't drop, really. That is one option. That is something in practice in spillways as well, but you could also look at other options like the OG shape. Okay, so that's one. Remember, I'm gonna continue to the next slide here. Now, one of the other things that we talked about was that coefficient that we have in the weir discharge equation. I'm going to write it up here. Discharge was equal to C times width times H raised to 1.5. As I said, that C value, you can't really theoretically estimate it, because the assumptions we made, velocity and head loss and so on, are not really easy to theoretically estimate. So what has happened is that there's a lot of data available that give us the range of these C values for different situations, different heads, like this table, width of the crest itself, and so on. And you'll see that 1.7, the theoretical value, is right here. And it varies from, as we said, really small, around 1.4, all the way to, I don't think we have it in this table, but 2.2 and so on. So it is a very relatively wide range, depending on the shape and how valid those assumptions are. Now, we mentioned that one application of these structures, weirs, one application is to measure flow, really. In this image, we have a V-notch, very, very common for measuring flow. So what happens is, if you measure depth upstream above the crest is your total head. You plug it into this equation, everything else is available or measurable, like width. And if you have a good estimate of C, then you can calculate discharge. And what is typically done is, obviously, as H or depth changes, discharge changes. So if you have a range of values for H and the corresponding discharges, you can develop a curve that shows us how discharge changes with water level upstream or head. And this is what we call a depth dash discharge relationship or graph or equation. And in many references and in many practical situations, this is also called a rating curve. So when you hear they say, oh, the rating curve for this station, this river, at this place is this graph, that's what it means. It means for different water levels, you can convert it to discharge. Measurements have been done and calibrated, so we have this measurement available. As we said, another very common situation where we have weirs is in spillways. You typically don't use spillways for measuring flow unless it's a really, really small flow and channel. They're typically used for controlling water level and discharging floods in a managed and controlled way, and storing water if it's a big reservoir for hydropower, or supplying or providing head to a powerhouse or things like that. So application is slightly different, but the same equation, nothing really different. And the same weir equations. C might be different again based on geometry and so on, but everything else is really the same. Another type of situation where you have slightly different from weirs, but in a way similar in terms of hydraulics is where you have choking, but here it's lateral constriction. This is what is used in what we call flumes in general. So basically, the width of the channel is reduced. In this image, maybe hard to see, but the width of the channel here is much smaller than the width of the channel upstream. Let's call this one B1 and then B2 or something like that. So B2 is smaller than B1. And remember from our choking studies before, if B2 is less than the minimum B, we get choking, the critical width of the channel. So that's exactly what happens in flumes. Very similar to weirs, you can create a hydraulic control, a critical section, and use this for measuring discharge and so on. That's exactly what happens in flumes as well. In fact, in this image, maybe hard to see, but there's like a scale or staff gauge or something upstream. This is probably what they use for measuring water level and then converting this to discharge using the equation. So very, very common. There is a kind of a customized version of flumes, which is called a partial flume. And it looks like this. And in plan, it is basically a lateral constriction in the flow. So nothing new. So flow goes from left to right, and we have a constriction, we have a reduction in width. And in section, they've combined this with something that looks like a hump. So what's going on here is that you not only have lateral constriction, but you also have change in bed. You have a obstruction along the bed as well. So a combination of the two. And what happens is obviously water level choking, we have choking flow, water level goes up, becomes critical, and then most likely you will have a supercritical flow and then a hydraulic shock most likely, but we don't know that. So you get critical depth. So by the way, this is plan and this is profile. So this is a kind of, again, the same idea, a measurement device, usually a measurement device for relatively small. I say relatively small because the one we have on the image is probably maybe a couple of meters long and maybe less than half a meter in width, but there are really huge ones, maybe 4 or 5 meter wide partial flumes, but again, not very common because maintaining these and managing these are not super easy. So not very common for measurement, at least in large canals and streams. But again, that's a combination of lateral constriction and blockage along the bed, a hump or something similar to a hump. Okay, so that's these are under the category of overflow structures, and all of them work based on the same principle. They choke the flow, create critical hydraulic control, and then you use it for whatever you want, measure flow or control upstream water level and so on. There's a quick question here. Yeah, go ahead.
Yeah, what advantage do we have constricting the flow both with like lateral and hump?
Yeah, so you can get it to work for a wider range of discharges. So if you only constrict it laterally or you only have a hump, you can only get the critical flow for a given discharge or slightly lower, higher, but combining the two, you can actually cover a wider range in terms of still having critical flow for a wider range of discharges. So that's kind of the advantage. Okay, so these are all under the category of overflows. Let's also look at underflows and start with orifice flow, which is kind of a good starting point. So what do we have? What is an orifice flow? As we saw, this is a case where the opening is somewhere in the middle of the flow field. So flow is not really going over the structure. It's actually going through an opening somewhere in the fluid domain. And it exits, and it's used again for the same idea of controlling water level or discharge or measurement and so on. So how do we deal with these, and what is the hydraulics behind this? Nothing really complicated here either. We have this, let's say this is a tank. The water level is up there. at a height of h from the opening, from the orifice. This is our orifice. And I'm going to use a very simple Bernoulli type equation. I'm going to pick a point at the free surface. Let's say this is 0.1. And then one right at the center line exit of the orifice. And I'm going to say there will probably be a streamline that goes like this. So I'm going to write the Bernoulli equation. Between 1 and 2, right? And what do we have? We have pressure at 1, pressure head at 1, height or elevation, velocity head, and then the same thing at section 2. So gamma h2 plus v2 over 2g. Now, with a bunch of simplifications and assumptions, we're going to say pressure at section 0.1 is 0 atmospheric. Velocity is almost 0 because water is almost stagnant. At section 2, I'm going to take the datum at the center line of the orifice, so this will be 0. And if you cut a section at the jet, at the exit, it will be exposed to air, so pressure here is also 0. So I'm only left with velocity head is equal to total head upstream. Or if we rearrange this, actually, let me use the subscripts 1 and h1. You will see that V2 will be equal to square root of 2gh. So what is this telling us? It says velocity at the exit of the orifice is equal to a square root of 2g times the head over the center line of the orifice. So very simple equation. Now, obviously, this is velocity. If you take velocity and multiply it by area of the orifice, you get the discharge. So A of orifice times square root of 2gh. I'm going to call this theoretical discharge. I'm going to tell you why in a second. And also highlight the fact that this is the area of the orifice. So if it's circular, if it's circular with a diameter of d, it's pi d squared over 4, or whatever shape it has. Okay, now here's what happens in reality. As the flow exits the orifice, I'm going to zoom in and show a bigger picture of the orifice. This is what happens. The flow is coming in. It's impossible for the flow and the fluid particles to make a 90-degree turn at the exit of the orifice at one section, one point. So in reality, this is what happens. The flow is coming in, turns around, it continues to accelerate a little bit. The same thing happens on the upside and continues, something like that. So what is going on? If you notice, in reality, the size of the opening, I'm going to say area, but this is section, so we know it's actually diameter, but for clarity, I'm just going to keep it as area. This is what the area of the orifice is. But in reality, that's not the cross-section of the flow. The flow area is actually this much. I'm going to call it actual area, which is slightly smaller than the orifice. And we know why. Whenever you squeeze the flow, the fluid particles, they need some curvature. They need some space. They need a little bit of, gradient, gradual change. The flow is not going to turn 90 degrees right away. Just like when you're biking or running or something, you can't really make a 90-degree turn at one singular point. It's impossible physically. So the flow continues to accelerate. As it accelerates, depth goes down until things balance out, and then the jet thickness doesn't change anymore, right? So that's why we are using the area of the orifice, but in reality, the area of the orifice is actually slightly smaller. So how do we deal with that? How do we fix that? The way we would fix that is we say, okay, let's take discharge and say it is equal to area of the orifice multiplied by square root of 2gh. But let's make a correction, add a correction and multiply it by the correction like C. Let's call it CD because it is the discharge coefficient. Discharge coefficient. Now, what is this discharge coefficient? It is kind of a correction because of all the assumptions we've made. What are the assumptions we've made and that are actually not super accurate? I don't want to say incorrect, but not accurate. The first one was the fact that the area of the jet is not equal to the area of the orifice, but we're using the area of the orifice as a cross-section of the flow. That is not correct. And the second one, just like a weir flow, changing energy between 1 and 2 is not zero. We assume it's zero, but again, in reality, it's negligible, but non-zero, right? So how do we deal with this? We introduce a coefficient called CD, and it's made of two parameters, two factors. One is C sub C, which is called the contraction coefficient. Contraction coefficient. What does it mean? It means exactly what we said. The area of the jet is not equal to the area of the orifice. So we have to correct it, apply a correction. That's called C sub C. And then the second one is C sub V, which is the velocity coefficient. What is that? The fact that velocity upstream is not really zero. It's non-zero, very small, but non-zero. It kind of correlates to the fact that head loss is not zero. It's kind of the same, but in terms of velocity. So I'm going to say this is somehow equivalent to energy loss or taken into account. So this will be our discharge coefficient for an orifice. Now, this diagram we have up there is showing 4 cases. Going from left to right, you have a typical very thin plate as the orifice. Your contraction coefficient is 0.62. 0.6, 0.65 is a typical value. So very, very common. You get 0.6 something. So around that number for contraction coefficient. As the edge becomes more streamlined and closer to what actually the fluid particles and the streamlines are going to do, the correction coefficient for contraction goes up to 1. So the second, the third, and the fourth one have a C sub C of 1. So the area of the jet is the same as the area of the orifice, and the last two. That's one. The next one is the velocity correction, CV, and its velocity correction is typically not very large. You see that it's 0.98, 0.98, 0.86, 0.98. So a few percent correction. It's non-zero, but not too big. And then CD, discharge coefficient, is the product of these two. And it's 0.6, 0.6, 0.86, 0.98. So slightly smaller than 1, but depending on CV and CC, it will be somewhere around there. So if you have absolutely no information, it is safe to assume that CC is 0.6, 0.65, and CV is around 1, because in most cases it's just below 1 anyway. So we're not making introducing a big error by doing that. Okay, so that's an orifice. Nothing new. It's really basic fluid mechanics. Now, one version of this, which is more practical and applicable to more open channel flow type scenarios and relatively large structures, is what we call a sluice gate or a slide gate. Sometimes you hear, and it's really the same idea as an orifice, but like half an orifice. So see the screen, the section we have here. Imagine we have that orifice. We have this slide gate, and it looks like this. It is very much like you have an orifice, and you basically have only one half. Let me show it. Maybe difficult to show it here, but something like this. and the flow is going like this. Obviously, we don't have any flow from the lower half of this orifice because it's the bed, but a slide gate is, or sluice gate is half an orifice, really. Nothing really different. Exact same thing happens. So if you see that's the water level, and you see what it's doing, the width of the, or the thickness of the flow, the depth is this much, and the opening of the gate is, let's say, W, and the depth downstream is a contraction coefficient multiplied by W. So slightly smaller than the opening of the gate, just exact same thing as an orifice, really nothing different. And this table at the bottom is showing the C sub C values. So this is CC, and it's the ratio of the area of the actual flow thickness or jet diameter or jet thickness to the area of the opening. And we see that it varies as the ratio of the opening to upstream head changes, but 0.6 is a good number, 0.611, 0.606, and around 0.6. So again, if you have no information, absolutely no data, very safe to assume that the depth downstream of a gate is 60% of the gate opening. That's what it means, roughly, right? So that's basically what it is. Now, how do we use this as again, a hydraulic control and structure? If we have a gate, very likely we're going to have the situation, we're going to have supercritical flow downstream because it's choking, and the depth of the supercritical flow will be CC, 60%, times the gate opening, right? That's what we have. So let's see how we use it and how we formulate this. So this is a sluice gate, section 1 and 2, upstream, downstream. And let's say we have, or we know the opening and CC, because we open the gate to W meters open, and CC is given, or we can assume it's 0.6. So let's see how we can use this to, again, as a device to measure flow. So we know that depth downstream will be equal to CC times opening. That's W. And this is Y2. And this is Y1. Okay, let's assume that we have no energy loss at the gate. So E1 is equal to E2. Okay, so what do we have? Upstream, we have Y, actually I should say Y1, plus rectangular channel Q squared, 2G Y1 squared, and right-hand side is, this is the specific energy equation. Q is the same discharge, 2G Y2 squared. Okay, now, as is, we can't really use this as a control. Why? Because we have three unknowns. We have Q, we have Y1, and we have Y2. But we know that Y2 is CC times W. So it's really not unknown. So if you plug that in here, let's see what we get. We have Y1 plus Q squared, 2G, Y1 squared. Okay, right-hand side, Y2 is CC times W plus Q squared, no change, 2G, and then Y2 again is CC times W squared. So what's happening here? Now, if you look at this equation, we have only two unknowns. We have discharge and depth upstream. Everything else is known because we have CC and W. W is the gate opening. If you're installing and operating the gate, you can open it to whatever dimension or opening you want. And also CC is either available or assume 0.6. That's a safe assumption. So for a given CC and W, we can measure depth upstream. Measure one, that's easy. You can just survey the water level upstream or have a staff gauge or something and measure it. And then plug it into this equation, calculate Q. Obviously, you can multiply by B, the width of the channel, and get capital Q, but that's a very simple calculation anyways. So this ended up being another hydraulic control because there's a direct relationship between depth upstream and discharge. So it is a hydraulic control. And if you recall, when we were looking at water surface profiles, in some cases we had a gate and we said, oh, we start from the gate because it's a hydraulic control. We didn't know why, but this should clarify, right? So in practice, again, gates, just like any other structure, are used for many different reasons, controlling flow and water level and so on. And sometimes what happens is that the gate actually is not a straight, simple plate. It's actually curvilinear, like the one we have on the image, like this one. So what that means is that if you look at the section of this structure, it might look like this. It might actually be something that looks like this. The gate itself is actually curvilinear. And this is what we call a radial gate. Radial gate. So that's the gate. And this gives you the opening at the gate. And this whole setup, sometimes we call it a gated spillway. So very common on some spillways, there are radial gates to, again, control water level upstream and so on. A question, go ahead.
Yeah, on the diagram it shows that y2 is equal to CD times W. Is that because we assume that CV is like really close to 1?
Oh yeah. So see, just like an orifice, yes, exactly. So CD is, if you remember, was CC times CV. CV is typically really small, and we sometimes tend to ignore it and say it's equal to 1 usually,
Okay.
and we assume it's 1. So if that's the case, then yeah, CD will be equal to CC. So sorry, I should have mentioned that. That's what's happening here.
Okay, thank you.
Yeah. Okay, so that's a gated spillway, very common. Many times we use these because it gives us some flexibility to control upstream water level, dynamically, and have that option to discharge and change the water level upstream. So very common. Again, nothing different. It will be exact same thing as we saw. It is an orifice, really. It's not any different, or a gate, really, and everything else will be the same. I have a couple of image clips here. I think they're going to be worth just looking at, just to give you a scale and dimension of things. This is a spillway chute discharging from a spillway. I just want to give you the scale. Look at the people on that bridge, and that gives you the dimensions of this flow. This jet might be, I don't know, 20, 30 meters tall, and yeah, this is another case. This is an outlet from a dam. So that's a dam, and that pipe coming out is an outlet for discharging water. And you see people on that platform. And the diameter of that jet is probably easily 5-6 meters. And the flow coming out is extremely fast, maybe 30 meters a second or something, which is very fast for water. Yeah, this one might be for just discharging water from this reservoir for different purposes, which I'm going to talk about a little bit in a couple of slides. But yeah, just to give you, again, some scales. This is another one, flow over the spillway of a dam. Unfortunately, I don't have the name of the dam, but this is, yeah, again, just notice the magnitude of the flow, the width. I don't think we can really see people on the dam crest itself, but yeah, maybe actually we can see this in zoomed in view. So see the people and then compare it to the dimension of the flow. This could be easily thousands of cubic meters a second. And look at the jet coming off the spillway. It's enormous, probably a very large flood. This is structure. This is another one. Yeah, OG spillway, very, very familiar shape now, right? Flow coming down, and then sometimes you see that this actually doesn't have a typical supercritical flow with a jump that we have been talking about. This is common. Happens very commonly in hydraulic structures. Sometimes they have these and they just discharge flow and let the jet interact with the air and dissipate, and then come back down, and almost a dissipated, almost like not a splash, but very much diffused and dissipated jet comes down. This is a 3-bay gated spillway. Look at the truck on the bridge, just to give you a dimension. And I think they're going to open the gates as we play this video. I'm not sure if they're going to open all of them, but this is a relatively large structure, spillway chute, and a gated one actually, and the gates opening. I'm not sure if it's going to show us all the way, but yeah, so that's basically just starting to operate. As I said, this is typically done to either bring the reservoir level down, or discharge floods or something. This is another jet coming out of an outlet. Again, look at the people and the dimensions of the jet. This is probably like 10-meter in diameter or something around there. Enormous jet. This is another flow looking down at the spillway chute. Again, it doesn't have that typical hydraulic jump. These are called flip bucket or ski jump type structure. So they basically discharge the jet into air. This one the same, and let the air do the job really to dissipate. This is another view. Again, enormous amount of flow at extremely high velocities coming out. And I think we keep talking about supercritical flow being a hazard in terms of erosion. I think that's a good way to visualize what we mean. This kind of flow, if you leave it alone, can erode everything downstream. So we have to manage it. Another view of a flip bucket type spillway. And all the white wire that you see is in a way good sign. It means that the wire is breaking into smaller and smaller drops and dissipating and losing its kinetic energy, most of its kinetic energy. There's another outlet. Again, a valve for a pipe. These are really orifices. They act just like an orifice. The spillway ones are like a weir. These ones are like an orifice. Again, that's extremely fast flow coming out of this. Yeah. There's another view. Go a little bit faster here. Yeah, this is another spillway. They're opening the gates and discharging onto the chute, and then farther downstream. Yeah, you see a lot of these structures have a combination of different discharge type facilities and structures. That's common for different purposes, depending on what you want to do with the flow and what the purposes could be. Different combinations of different components for discharge. See what else we have. Yeah, bunch of jets here again. This is let me go back actually. This one has a bunch of gates, and again, they open the gates and discharging from the upper level. This is another big structure. Yeah, one more here. This one's another outlet discharge, an orifice, really. It's an orifice. The reason why the flow is doing that is splitting like that is because there's a valve inside. It actually, that's intentional to break the jet into, again, smaller drops. This one's a very violent hydraulic jump. So what we're looking at is was a hydraulic jump, but definitely not a stable one. Very, very violent and very turbulent. Another discharge structure. This one's an interesting one. This is a stepped, almost a stepped spillway. So this is again relatively common. Instead of having one chute with one smooth surface, you have a bunch of steps, and each steps basically drops lower down and then dissipates a little bit of energy, and you keep doing that on a bunch of steps until we reach the bottom of the spillway. Yeah, so yeah, just to give you an idea of in particular the scale of these structures, and as I said, it could be a simple 0.5 meter weir in a tiny channel all the way to a 50-meter wide spillway with thousands of CMS. It's the same idea, but different scale, of course. One more thing I wanted to mention is what the upstream side of these. I think some of you will study this later in 416 if you take that course. But this is the intake side of the outlet, let's say. So the flow goes into this tower in here. This is the reservoir, flow goes in here, and then is discharged downstream, just like an orifice. But the intake itself could be relatively complicated in terms of hydraulics because there's air, there's turbulent flow going in, and it's typically not a straightforward in terms of design. But what I wanted to highlight here is what is called a selective withdrawal. So your reservoir level will be at different levels during different seasons. And even at one season, one day, let's say, at different elevations, different depth in your reservoir, the water characteristics are different in terms of quality, temperature, and so on. So sometimes for different purposes, we want a specific discharge from specific layers, the stratified layer in the reservoir. So the way this is done is using what is called a selective withdrawal type intake tower, which means you basically have gates at different elevations, and they help you withdraw from whatever elevation you want, depending on the temperature or the quality or density or sediment or whatnot. This is what it looks like. This is a relatively simple one, so maybe hard to see, but you have, let me highlight it. Oops. You basically have, see, there's one inlet here, and then another one here, and then there's some more down there. So at different levels, you have different intakes. This is another one with way more intakes from all the way at the bottom. You have probably 20, 30 intakes, and that gives you more control on how you can withdraw from different depth. And again, different depth means different quality and temperature and so on. This one's another example. It might be Hoover Dam, I think, but I might need to confirm. But again, the 4 intake towers on either side are basically selective withdrawal type features. This is another example. Most of them, you see, they have like a trash rack. So that's what is used to keep the debris and trash. And sometimes there are big trees coming down or, you know, different things. So you want to keep them out. That's why they have that. Not in this case, but sometimes you have these screens to keep fish away, you know, that kind of application. This is another one with kind of a zoomed in view with the bigger trash racks, quite obvious. This one's not operating, or I think during construction or something, but that tower in the middle is the intake tower, and they have intake at different elevations. And as you can imagine, when this reservoir fills up later in future, you will have different heads at different elevations, and that will give you different discharges. So you can have, again, some options, some flexibility in how you're withdrawing from the reservoir.